11 machines and expeditions by which people actually measured the deep ocean. Not folklore, every one of them a real device with a name and a working date. I don't mean stories told about the deep, I mean the actual instruments. A hull plate, a drifting robot, a satellite, a steel cage built to hold ordinary bottles. Every one of them also corrects something people assume without ever checking it. We start in the North Atlantic in 1929 with 12 telegraph cables. 12 transatlantic telegraph cables snapped in the North Atlantic on 18th of November 1929, one after another rather than all at once, off the south coast of Newfoundland. A magnitude 7.2 earthquake had struck the Grand Banks region minutes earlier. But the cables did not break where the quake hit, they broke one at a time, moving away from the epicenter. Nobody was down there to watch whatever happened next on the seabed. The only record left behind is a timeline of breaks strung along a known cable route, and that plain timeline turned out to be worth far more than anyone laying the cables expected. This is a cable ship's own deck in that same era, 1924, crew hauling cable by hand, coiling it before it winds onto the drum, the ordinary work behind laying a line like the one that failed in 1929. The cable break times were the only instrument that recorded the slide, each break a stopwatch click at one already known point on the seabed below, nobody present to see it happen. This is a modern armored cable cutaway, shown here for the construction, not the decade. Steel wire wound tightly around a signaling core, built to survive being dragged, buried, and repeatedly repaired at sea. A broken cable carries a time stamped by the company, logging the fault, and a fixed position on the seabed from when it was laid. Line up 12 of those in order, and a landslide with nobody watching gets a timeline. This is the kind of sloped, sediment-covered seabed a cable route like this crosses, exactly the terrain a slope failure could travel across without anyone above ever seeing it move. The nearest cables broke almost together, within minutes of the quake. Then the breaks kept arriving, later and later, the farther out on the slope a given cable lay, as if something had physically traveled outward and cut each one as it passed. This is a preserved chain grapnel, the tool a repair ship dragged along the seabed to hook a broken cable and haul it up to the surface for splicing. A 1952 study argued for a fast-moving flow down the slope. A later paper reopens the earliest breaks so the true speed stays disputed. The tsunami it triggered killed 28 on the Burin Peninsula, 27 drowned, and a girl who died of her injuries in 1933. A ship can map the sea floor without ever touching it, using nothing but a fan of sound fired straight down from a plate bolted flat to its own hull into open water it will never have to enter. This is exactly what that mapping produces. Pattern seamount in the Gulf of Alaska, rendered in false color from real NOAA survey data, red for shallow, blue for deep, the whole shape built from one ship passing overhead. A sonar image of the seafloor is not a photograph of anything down there at all. It is built entirely out of timing, how long each of hundreds of separate sound beams takes to leave the hull, strike bottom, and travel back up. Hull-mounted sonar transducers bolt on flat like this dome, photographed in dry dock on a naval vessel. The same basic fitting any hull-mounted sound source depends on. One pass over a seamount can paint a swath several times wider than the water is deep, because the fan of beams spreads wider with distance, the same way a flashlight beam widens farther from the bulb. This is a real submarine canyon mapped the same way. Mona Canyon, rendered in false color from an actual multi-beam survey, cut walls and a channel floor built entirely from travel time, no diver or camera anywhere near the seafloor itself. Turning that travel time into an actual depth number needs one more piece of information. How fast sound is moving through that particular column of water, at that exact place and moment. That number is called the sound speed profile, and it is never fixed. Temperature and salinity change it by depth, by season, by location, and the survey software has to be told which profile actually applies right now. Get that assumed profile wrong, and the seafloor drawn from it bends. A real ridge can appear to shift sideways, A genuinely flat plane can sag into a false trench, and nothing in the finished polished map ever warns you that it happened. This is the instrument that profile depends on. A NOAA crew launching an expendable probe by hand off the stern, recording temperature down through the water column before the survey begins. Routine coverage reaches roughly 2 to 4 times the water's depth in swath width per pass, enough to map a seamount in one line. Given the right sound speed profile, the method is fully explained. In 1961, a ship held itself steady over one exact spot in deep open water with no anchor chain anywhere near long enough to touch bottom, so a drill bit could reach down toward the mantle underneath it. This is that same ship, Cuss Y, in an archival image from the drilling itself. A converted vessel holding position over open water instead of riding at anchor, the way any ordinary drill ship of the time would have. Holding a hull steady over one single seabed point, in water that deep, with no anchor line remotely long enough to help, meant solving a genuinely new engineering problem that nobody had ever fully solved for a working ship before that specific attempt. This is the kind of basalt a hole like that actually pulls up. Dense, dark, unmistakably different from the soft sediment sitting above it. Real oceanic crust, not seabed mud. The wider project had been proposed back in 1957, and a committee took formal charge of it in 1958. 1961 names only this one Guadalupe drilling phase, the specific part that finally put a bit into real rock. Keeping the ship over that single spot took constant small corrections from its own propellers and thrusters, someone watching the drift and pushing steadily back against it second by second for as long as the drilling itself continued. Nobody has drilled through the crust into the mantle, not then and not since. Moholy reached basalt and stopped right there, a sample of the crust, never an actual hole all the way through it. This is Guadalupe Island itself, seen from orbit, the volcanic island near the drill site, chosen specifically for its unusually thin ocean crust and its deep, calm, workable water. $57 million had already been spent by the time the whole project was cancelled in 1966. Separate estimates for actually finishing a full mantle hole had climbed from an original $14 million toward a projected $160 million, a larger, different number describing a cost that was never actually paid. What survived Moholy was never the hole itself. It was dynamic positioning, holding a ship steady over one seabed point using only its own engines, a technique the entire offshore drilling industry still runs on today, decades later. The mantle itself is still never touched directly by anyone. Every station on this list still measures it only from above, the same way Moholy once tried to reach it from a deck floating over open water. A hole that reached rock, but stays disputed as any kind of finished attempt on the mantle. Roughly 3,600 robots are sinking and surfacing in the open ocean right now, entirely on their own, with nobody anywhere actually driving any single one of them. This is one of them on a research vessel's afterdeck before deployment. A slim cylinder about the size of a person, no engine, no propeller anywhere on it, about to be lowered over the side and left alone for years. Before floats like these existed, almost nothing measured temperature below the surface except a ship passing through with a single line over the side, once on its way somewhere else entirely. This is that same design, freshly deployed, floating at the surface in open water moments after release, right before it takes on ballast and begins its very first dive. Each float runs the identical 10-day cycle, sink to a parking depth near 1,000 meters, drift there quietly with the current, then dive further down to 2,000 meters before finally turning back upward. On the way back up, it measures temperature and salinity across the entire climb, surfaces, radios the whole finished profile up to a passing satellite, and sinks again to start that same cycle over from the beginning. No ship, no crew, and no fixed schedule at all. Just a small buoyancy engine repeating the same patient climb worldwide on its own internal timer for the entire working life of that one float. Thousands of these floats are scattered across every ocean basin at once, spaced far enough apart to cover the whole open ocean without any single float overlapping another's patch of water. The array reached its planned size of 3,000 floats in October 2007, the first point at which the open ocean finally had a standing network, instead of only scattered ship visits now and then. This is one float opened up, its own internals exposed dockside, the buoyancy bladder and small pump that changed the float's total volume just enough to sink or rise on command, with no moving fins or thrusters anywhere on the actual hull. The standard array still only reaches 2,000 meters down. By the program's own description, these floats sample only the top half of the sea, a buoyancy cycle that is fully explained, even though it still only covers half the water column. Most of the seafloor map you have ever actually looked at was never sounded by anything at all. It was drawn from space instead, without a ship anywhere near most of it. This is exactly that kind of map, a full gravity anomaly rendering of the world's seafloor, ridges and trenches and seamounts, all traced out from satellite measurements of the sea surface, not from soundings. A satellite measures the height of the sea surface itself to within a few centimeters, and the seafloor underneath shows straight through that height because mass pulls water gently toward it. This is one of the satellites that actually does that measuring, shown in an official rendering tracking sea surface height along repeating ground tracks for years at a time across the whole ocean. A seamount's own gravity pulls a small real mound of water directly above it. A trench does the opposite. Less mass sitting below means a shallow dip in the surface directly over that gap. Millimeters of sea surface bump or dip translate directly into an estimate of the seafloor's own shape underneath. Everywhere a satellite has ever flown, without a single physical sounding taken at most of those exact points, the data behind that estimate is filtered to a 16 to 160 kilometer wavelength band, fine enough to reliably find a seamount, far too coarse to trust for anything smaller than that scale. Across an entire ocean basin, that same signal shows up as broad bands of slightly higher and slightly lower water, standing out clearly once enough satellite passes have accumulated over the same stretch of sea. Real physical soundings still matter enormously because they remain the only way to check the gravity estimate against one actual measured depth at a single point, then correct the wider map around it. A single ship crossing that same stretch of ocean, once with its own hull-mounted sonar running, can lay one real measured strip of ground truth across a much larger unverified estimate. Only 27.3% of the seafloor had actually been surveyed to modern direct sounding standards as of June 2025. Whatever fills the gap between soundings stays genuinely open. Those 5 are the machines built to answer one large question apiece. The rest of this list is smaller gear, doing work every bit as strange in its own quiet right. In 1992, a shipping container went overboard in a North Pacific storm, spilling 28,800 plastic bath toys straight into the open ocean current. That spill happened on 10th of January 1992, near 44 degrees north, 178 degrees east, a single recorded position that became the starting point for tracking every single toy that followed afterward. Beachcombers who later found a duck or a frog on a shoreline reported exactly where and when, and oceanographers eventually turned thousands of those small reports into genuinely real drift data. Nobody photographed the actual container going over the side, and no free image of that moment exists anywhere. This entire reconstruction runs on drift models and the beachcombers' own scattered reports. Some of the oldest working instruments on this whole list are just plain stone buildings. Harbor gauge houses, built purely to hold one float perfectly steady while the open sea outside does whatever it happens to be doing that day. This is the kind of stone gauge house harbors like this have used for over a century. A stilling well built into the harbor wall, letting water in slowly so chop and passing waves never reach the float sitting quietly inside. Brest, France has run one continuously since 1807, the longest continuously operating true tide gauge record in the entire global archive, though Stockholm's own gauge, running from 1774 to 1984, makes exactly the same claim for itself. A maregram is the paper trace an older gauge draws entirely by hand. A pen riding the float's own slow motion, sea level charted as one continuous line with no gap in it anywhere. The single most used instrument in all of oceanography is not exotic in the slightest. It is a steel cage built purely to hold a ring of otherwise ordinary bottles. This is a real CTD rosette sitting on deck, a dozen or more sampling bottles mounted in a circle around one central frame, each bottle open at both ends, simply waiting to be closed. Sensors built into the frame read conductivity, temperature, and depth continuously as it descends, and a scientist watching on deck uses that live feed to choose exactly which depths actually matter. This is that same kind of rosette entering the water at dusk, lowered on a bare wire, bottles still open, beginning the descent where each one gets triggered shut at its own chosen depth. The standard float fleet stops cold at 2,000 meters down. A newer class of float keeps going far past that exact line. This is a real deep Argo float being lowered from a research vessel, a heavier, thicker hulled version built with a pressure housing rated for far greater depth than its shallower cousins. The newest of these floats are rated to 6,000 meters. Some earlier models, still working in the same program, reach only 4,000. Two separate depth classes, never one single flat number. Most of the ocean's actual total volume sits below the standard array's own working floor, so this entire class exists purely to reach the water column the older fleet was built to simply ignore entirely. Depth itself is not a fully solved engineering problem. One single vehicle proved exactly how unsolved it still actually is. This is Nereus itself, hauled back aboard its support ship after an autonomous test dive in October 2009. The same year it reached 10,902 meters at the deepest known point of the Mariana Trench. It carried thick-walled ceramic spheres built specifically to hold delicate instruments intact under crushing full ocean pressure. The same punishing pressure class the trench's own deepest point sits permanently under. On 10th May 2014, 7 hours into a planned 9-hour dive in the Kermadec Trench at around 9,190 meters, contact with it was lost entirely. What came back up to the surface afterward was scattered debris, not the vehicle itself. Sound does not simply spread outward and fade with distance underwater at all. There is one particular depth where it gets trapped completely instead. That depth is the SOFAR channel axis, roughly 700 to 1,200 meters, depending on latitude, shoaling steadily toward the surface at higher latitudes closer to the poles. At that exact depth, sound rays bend back toward the channel's own axis instead of ever escaping upward or downward, so the energy stays trapped inside it and travels enormous distances with remarkably little loss along the way. In 1944, a small charge set off at that depth was heard clearly on a hydrophone thousands of kilometers away, and in March 1960, a signal from Perth, Australia was heard on a receiving station nearly on the opposite side of the entire planet. Telegraph cables timed a 1929 landslide nobody actually watched, and the true speed is still disputed. Multi-beam sonar reads the whole seafloor in sound, fully explained, provided the sound speed guess underneath it is right. Mohol once held a ship over open water, trying to reach the Mantle. Disputed because nobody has actually gotten there yet. Argo floats keep the open ocean's temperature record running entirely on their own. Fully explained, and satellite altimetry reads the seafloor's own shape from the sea surface itself, leaving what is genuinely still open. Most of that map was never sounded by anything at all. If machines measuring the parts of the ocean nobody can actually see are worth your own time, subscribe. There are more of them waiting, and at least one of these still has no fully settled answer at all.